Hello student, welcome to the first lecture in the first module of this lecture series on college algebra. In this module, we will study about linear functions and equations and inequalities that are based on linear functions. Now that means we will have to study what functions are first, right? And the concept of functions is, we will come to the details later. The basic idea is there are inputs and there are outputs, and you match the inputs to outputs, right? That is basically a function. Now, that can be done with any type of objects. If you go to a grocery store and there are fruits and vegetables, right? Apple, oranges, broccoli, and for all of them, there are prices listed, right? Per pound, let's say. And you can now create a function with those grocery items and their prices. But you can also do this, right? Those grocery items, if you note them, most of the fruits and vegetables, they will have some number, right? Code. So instead of representing it give by its name, you can use that number and match it to its price. Now it becomes a function from numbers to numbers. And why is that important? Because in real world, we are going to apply, as I said in the introduction of this lecture series, we are going to look at real world applications. But in order to apply to the real world, we model that real world situation using mathematics. And in mathematics, we use numbers. Okay. So when we study functions, functions can be in general defined from any objects to any objects. But in mathematics, we use numbers to represent those objects. Hence, to understand and analyze functions, it becomes important that we understand numbers and we are familiar with the different types of numbers. Okay. And I was also talking about the input and output idea. If we want to now represent visually, again, remember, a graphical approach is a crucial approach in this entire course. So if you want to represent visually, you would represent the inputs on one direction and usually use horizontal axis for inputs and vertical axis for outputs. And that is a coordinate system. Okay, and we also need to understand how coordinate system works, the basics of coordinate system. So all of these will be foundations to understand functions. Okay. So once again, I will summarize what I said so far. We are going to study linear functions and equations and inequalities based on them. To understand linear functions, first we need to understand functions. To understand and study functions, both analytically and graphically, we will need to understand the numbers and the coordinate system that is based on the real numbers. Okay. Hence, let me begin with the first topic in this module, real numbers and the rectangular coordinate system. Okay. So what do we have here? There is a table here of the sets of numbers. Okay. And this table will start with the smallest set that we normally use, and then gradually add more numbers and make a bigger and bigger set. The first set of numbers are natural numbers. They are called natural because they were developed very naturally when civilization developed. Okay, that is one way to understand why they will be called natural numbers. It comes naturally to you, like how many fingers do I have? 1, 2, 3, 4, 5. We would count like that, right? So the numbers here are 1, 2, 3, 4, 5, 6, and so on forever. Okay. They are also called counting numbers for that reason. Another name for natural numbers is counting numbers. And the notation, because in mathematics, we use notations to simplify things and make it easy to write. We use the letter n. Actually, it's called script n with that extra line. Okay, that represents the natural numbers. Then whole numbers. Now we started with counting. If you have, when the civilization began, if let's say you're a farmer and you had some cattle, you have 1, 2, 3 cattle, right? What if you don't have any cattle, right? Then you would need to represent that by a number 0. Okay. And with that, you include the natural numbers. That will be called whole numbers. Just the extra 0. And the letter used for whole numbers normally is W. Now, here is a small clarification I should give you. In some textbooks, you won't find a mention of whole numbers. Okay, these two are often just called natural numbers. Okay, so some textbooks will not mention whole numbers. The 0 is included in the natural numbers, and 0, 1, 2, 3 is considered natural numbers. And actually, that is that is more accepted now than using whole numbers separately. I'm saying it here because our textbook has the whole numbers there, the one that we are following for this course, for the homeworks for this course. But know this so that if you see that 0 is included in natural numbers, don't fight with it. Okay. All right. Next, integers. Now, I was saying, if you don't have any cattle, you have 0 number of cattle. But what if not only you don't have cattle, but you had borrowed some from your neighbors in the past, and now you owe them back? Barter system, right? Now that is how do you represent that idea? You owe something, and that would be a negative number. Okay, so all the way from negative infinity, let's say, to -3, -2, -1, and then include what was there before, the natural numbers, 0 and the positive natural numbers. Okay, those will be called integers. Our notation for the integers is G. Okay, maybe G for integers, again, script G with that extra line. I would write a description also here. As I was saying, these are negative natural numbers, 0. Okay, I should use the symbol 0 because the word 0 has a different meaning. We will see that very soon. 0 and positive. I'm using shortcut. Okay, natural numbers. Okay, rational numbers. Now, even that is not sufficient, as where civilization is progressing, right? We need to talk about fractions now. Okay, not for cattle. Let's say a loaf of bread. You are sharing that among 3 friends. How much bread each person gets? You will say 1/3, right? That is a fraction. Those will be called rational numbers. And in the rational numbers, you see this word ratio, which is actually the reason they are called rational numbers. ratio null numbers, rational numbers. Okay, so it is not about rational and irrational. Many people tend to think that. Okay, so this might be a good, knowledge for you to sometimes to explain to your friends. Okay, so what is the rational numbers? Fractions, right? Now there is going to be something different. You will see now. Okay, I don't know where to start or what to write first. I'll just let's say leave it like that for now. Okay. Uh, Compared to natural numbers, whole numbers, and integers, where it was very easy to write in that order. Although in integers we had already seen, some complication about extending to infinity on both the sides. But when it comes to rational numbers, again, like you would start from negative infinity, go to positive infinity, but you have all these fractions in between. How do you order them? Okay, that is a very interesting topic by itself. Those of you who are interested, I would recommend you do some additional study, watch some videos on that. There is a concept called you have as many rational numbers as you have natural numbers. Actually, okay, it's not that you have more rational numbers. You cannot say that. You have the same amount of, I would say, the natural numbers and rational numbers. How is that? That's a very counterintuitive idea, which means for every rational number, you can find a natural number. Okay, how that works, and which means I will be able to write the rational numbers just like natural numbers, starting with in some kind of logic, okay, starting with the first number and then continuing from there. We can do that for rational numbers. Watch some videos on that. Okay, the words you might want to notice is countability. Do some research on this idea called countability of numbers. Okay, rational numbers are countable. Okay, so the rational numbers are basically fractions, not just any fractions, fractions of natural numbers. That is important. Okay, positive or negative natural numbers, integer in general. So it's not like you can do 1 over root 2. 1 over square root of 2 is not rational number. Okay, 1 over 2 is a rational number. And the notation for rational numbers is Q. Then what are irrational numbers? The simple idea here is you are now looking at what is called complementation. No, you have all these rational numbers, but still it is not enough. There are some other numbers which are not even included in that. What kind of numbers? Things like square root of 2. Okay. Now, why are they different? Why can I not write square root of 2 as one of the fractions? Again, another topic for you to study. Very interesting topic. Okay. But it can be proved. It can be proved that square root of 2, there is no way you can make it into a fraction. Okay. And these will be called irrational numbers. That is just one example. You have actually more irrational numbers in some sense than rational numbers. And let's say 1 over square root of 3 and so on. Even negative. Okay, you can put a negative sign here. And maybe I will list two numbers here. Two of them are pi and e. These two you will be using frequently in mathematics. Pi 3.14 and e, many students, everyone knows pi, the number pi, but some students will not know the number e. So again, good knowledge for you here. Euler's number, it is called. Okay, after the mathematician Leonhard Euler, we will be talking about that also later in this course. That is also an irrational number. Okay, and what is the notation for irrational numbers? T. Okay, then comes real numbers. What are real numbers? Put them together. Rational plus, I would say, okay, in very informal language, irrational. That is real numbers. So real number should be all possible numbers you can imagine, okay, in real world. And the notation is R. Okay. Now it turns out that even that is not enough to represent all possible numbers. There are something called complex numbers. And the idea of complex numbers, all up to now, okay, up to real numbers is comes from real world. Like you start, as the civilization developed, as I was saying earlier, right? People had to share a loaf of bread, so you can talk about fractions. You might wonder, where does irrational number comes in nature or in real world? Simple example, many of you know, have heard this, the Pythagoras theorem, right? And if you have a, let's say, a triangular plot of land, and you had two sides, 100 meters by 100 meters, what is the length of the diagonal you have? That is going to be an irrational number. Okay, so in real world applications, the irrational numbers will arise. The number pi, it comes in real world, right? Circular things, and all of them appear in the real world. They are real numbers. Complex numbers are purely the creation of mathematicians. Okay, you don't. Again, somebody might argue that in to understand or to explain many things in real world, in physics and astronomy, you will need the complex numbers. But again, like now it's not that real. Okay, somebody has to imagine here. These are complex numbers. What are complex numbers? First of all, the basic idea of complex number. I'll just get into that. We will study this in detail later on in another chapter, I think chapter 3. But for now, the basic idea is, if you have to take the square root of a negative number, then you are now in the complex category. Okay, why? Because whenever you square anything, it becomes positive, right? So what does it mean to take the root of a negative number? How can that even happen? That is the idea. Okay. And another thing you might want to just make note of for now is complex numbers are written like this: a plus ib, where I is this number, square root of -1. Okay, the letter I is used for that specifically, and you write complex numbers as a plus ib like that. Okay, and example, let me write an example like 2 plus 3i would be a complex number. I'll just leave it at that for now. As I said, we will study more later. The notation for complex numbers is again a letter C with a cut, script C. Okay, not exactly cut. That is when I write by hand. Um, in in mathematical font on a digital platform, you will see a C with that extra line, just like R or G. Okay, and now you will notice that on the list of notations we have on the right side here, this is a script, this is a script notation, this is a script, this is a script font, right? And actually, those are the very standard symbols. So whenever a R like this is used in any mathematical context, you immediately know we're talking about real numbers. Okay, it is super standard. W, Q, T, not like they're not standard, they are, but not that very standard. Okay, so in some textbooks, we don't use those letters. Instead, we say what is not rational is irrational, and there are ways to represent. Okay, all right. Here is a very interesting set of practice problems. I will start solving some of them and then I will ask you to complete the table and check with me. Okay. We will take each of this number here and classify it. Which categories does it belong to? Let's say the number 0. And I will now go with that updated definition which I was saying. Sometimes 0 is included in the natural numbers. Okay, let's go with that. So it is a natural number. It is a whole number. In fact, in the concept of whole numbers, 0 is included and it becomes whole numbers. Is it an integer? Yes. See. So all integers are rational numbers, but rational numbers are not irrational numbers. Okay. But rational numbers are real numbers. And here's the thing about complex numbers. Every number is a complex number. Okay, so even the real number 0 is a complex number because you can write this 0 as 0 plus 0i. I said we can write as a plus ib. So you can write as 0 plus 0i. So in that sense, it is a complex number. And that is true with every number. Okay. Right. Next, -1. It's not a natural number. Natural numbers are only positive integers, right? It's not a whole number. Again, whole numbers means starting with 0 at the least, but it's an integer. It's a negative integer actually. Integers are rational numbers. Okay, I was saying about this earlier. You might wonder why rational numbers should be fractions, right? You can write that -1 as -1/1, right? Okay. So in that sense, it is also a rational number. So it's not irrational, of course. It's real. Every number is a complex number. Now you can actually go ahead and try to complete as much as you can. And if any of them is not clear to you, then you can wait for my explanation. Okay. 2/3, it's not natural, not whole number, not integer. It's a rational number. So it is not irrational. It is real. It is complex. Okay. Next number is -4.13, where now I'm going to talk about some important thing. Okay. This number here and this number here, both are decimals. The one that you see up here is what we call a terminating decimal, right? 4.13, that's it. And those terminating decimals are rational numbers. Okay, so clearly, it's not a natural number or whole number or integer, but it is a rational number. Which means you will wonder, that means it should be possible to write that number as a fraction, right? Terminating decimal is very easy because you can say it is -413 divided by 100. Right? Easily you can convert it into a fraction of integers. Hence it is a rational number. So it's not irrational, it's real, it's complex. Then what about the next number, 0.6 bar? This bar notation, again, you might know it already. If you didn't, here's your opportunity. That is the notation for recurring decimal. Okay, so 0.6 bar means 0.66666 forever. And it turns out that is also a rational number. opportunity for you to again watch some videos how to convert 0.6 bar, or just do a Google search or on any favorite AI platform that you have. It will give you a simple explanation. Okay, that 0.6666 can be converted into a fraction. I will tell you, it will be 2/3. Easy to guess. Okay, and hence it is a rational number. Note down the words. Okay, terminating decimal and recurring decimal, they are rational numbers. So this remaining part of that row you can understand. Let me write the word here so you don't miss it. Okay, the one here is terminating, and 0.6 bar is recurring. So it means non-terminating. Okay, recurring, non-terminating decimal, they end up becoming, all of them, okay, end up becoming rational numbers. What about pi? I had earlier given an example, that is a classical, one of the basic, most commonly I would say used example of irrational numbers, pi. And then you will wonder, how can you say that? I have seen the value of pi, 3.14. You would have used it in your high school to find the area or circumference of a circle of radius 7 centimeters or something like that. 7, right? Because 22/7 and it easily cancels. Or you might have used this fractional value. The thing is, these are approximations. Okay, 3.14 or 22/7 are not exact values of pi. Those are approximate values, near values. The actual value of pi will have many, many more decimals. I think we use that on the next page again. 3.14159 and so on. Okay. People have used supercomputers to compute trillions of decimals there. And the thing about this decimal compared to the ones above is, these are not recurring, non-recurring. I'm writing at the bottom of the page here. Okay, so these are non-recurring decimals, which means you will never find the same numbers, same block of numbers repeated again and again. Okay, these are non-recurring decimals, and those are irrational. Okay, so none of these categories will apply now, but irrational numbers are real numbers, and every number is a complex number. Okay, similarly, square root of 2, again, approximate value 1.4142, but the decimals will continue and they will not repeat. They are called irrational numbers. Root 2 is an irrational number. So none of these, it's an irrational number, it's a real number, it's a complex number. Okay. Then you see root 9 and you will wonder, negative root 9. Okay, root 2 is irrational. So every root is irrational, right? No. Square root of 9 is 3. So don't go by the look of it. You have to simplify and see that if it is actually irrational. Okay. So if you cannot get rid of the roots, that square root sign or cube root sign, whatever it is, if you cannot get rid of it, even when you try to simplify, then it is irrational. Okay, not otherwise. So in this case, actually, it's not natural number or whole number, but it's an integer. But because it is an integer, it is a rational number. So it's not irrational. It's real and complex. Okay. 2 minus 3i. I had said earlier, that's an example of complex number, which is not real. So none of this will apply. Okay. So just because you see I in that expression, don't conclude immediately that it's going to be a complex number or not real number. How do you know? I will not prove it to you right now, but you, for now take my word for granted, in faith. We will study this later in the course. You'll find that 1 minus I and 1 plus I, when you multiply, it will end up becoming 1 square plus 1 square, 2 square, 2. Okay. And that 2 is an integer. In fact, it's a natural number. It's not irrational. Okay. And just the number I is called pure imaginary. Maybe I should have used a different color here now that I think about it. It's called, if you just have I, no, like a separate number without I, like 2 minus 3i has 2 and 3i, that 2 is called real part, 3i is called imaginary part. More about that later. But if you have only I, we call it pure imaginary. Okay. It's a complex number. And it doesn't belong to any of this category. Okay. That is the classification of those numbers. Here I wanted to give a little bit, extra information about how we represent these sets of numbers. Okay. So in the table above, you saw that I try to list them. Sometimes, I explained why it will not be possible to list all of them, right? We just wrote basically examples and some description of what those numbers are. There is another very useful and very popular method of representing these sets or any other sets called set builder method. Okay. So for example, or I would say the best example in this context is going to be the rational numbers. This is how we can express it. Okay. I will say the rational numbers. Now notice that bracket. It's called the what we call the flower bracket or braces. Here I would say set bracket. Okay. So we use that to denote sets. And here I'm going to write A divided by B. Because that was the idea of the rational numbers, right? Fractions. And what are those A and B? We use this line, which is read as such that. Or sometimes people also use colon, okay? The 2 dots, colon. A over B such that A and B are integers, right? But that's not enough. You have to say one more thing. That let me erase this such that. So that particular line is read as such that A and B are integers, B is not 0. You cannot divide by 0. Okay. And then close the bracket. 2 brackets, and inside that you write this description. It is called set builder notation. Okay. So this is a set builder notation. As the name says, it gives you a method to build the set. Okay. So some sets are expressed more easily this way. We could not list all the rational numbers, right? Or we could not even show a pattern. For natural numbers, if we say 1, 2, 3, and so on, there is an ordering there. It's clear, what numbers we are listing here. But it's not that easy for rational numbers. Whereas this set builder notation makes it more clear, right? What exactly are the numbers we are going to include here. So that would be the reason why set builder notation is useful and why we study it. Another example, the complex numbers. Right? I said all the numbers of the type a plus ib. So formally in set builder notation, you will write like this. Use the set bracket a plus ib. All numbers a plus ib, right? Such that, as I said, colon is also used for such that a and b are, this time I'm going to use this way of writing in R, which means a and b are real numbers. Okay. Those will be complex numbers. So that is again building the set. It gives you a formula or a rule how to write or not write, how to know what elements belong to that set. What numbers belong to that set. This is a set builder method. It gives you a formula for that, a rule for that. All right. Let's move on. Now we have studied all these numbers, the number system. Let us look at the real numbers again. Complex numbers, we will come to that later. But just before complex number, the biggest set was real numbers, right? Which included all possible numbers in real world. And hence, we also want to look at it visually. Many times it will be easy to look at numbers visually. The set of real numbers is represented graphically, which is mathematical way of saying visually. The set of real numbers is represented graphically using the what we call number line. Okay. And what's a number line? Here, it's very simple to draw. Negative infinity, by the way, that's the notation for infinity. Positive infinity. Okay. And that line, arrows indicating that they continue forever, and everything in between, that's called the number line. We often represent one more number here, let's say 0. Every point on the line represents a real number. Okay, think about that here. If I mark any random point, let's say here on the line, it is some real number. Okay, and for every real number, there is a unique point on the number line. This sentence is very important. Okay, the real numbers and the number line have this one-to-one relation. Now, take a real number, you can find a point for that on the line, and there's only one point for that number. And if you take a point on the line, there is only one number which it represents. Okay. In fact, the number line can serve as a coordinate system for one dimensional. Now, these are some extra words I'm using here. Don't worry too much about it. Okay, it's a good general knowledge, so I wanted to mention it here because we are going to talk about the rectangular coordinate system soon. I thought it will be good idea to tell you that coordinate system in general can be in any dimension: 1 dimension, 2 dimension, 3 dimension, n dimensional, and even infinite dimensional if you do higher mathematics later on. Okay. Now, what is 1 dimensional space? Let's say, you are on the highway, straight highway, or even if it is curved, let's say, until you take the exit, you are going to be driving on the highway, right? Okay, in that case, you can actually only drive in the forward direction. Or if you look at the highway with both, north and south or east west, let's say, you can move in the forward or reverse direction, but it's the same line, right? So that is the 1 dimensional space. There is only 1 dimension, only one direction of movement. And in that 1 dimensional space, you can pick any one point, let's say, and call it 0, the reference point. Anything north of that is positive. Anything south of that is negative. Say, you come up with that convention. Then that number line. You can now use the number line to represent this space. And any point on the space now coordinate. We call it coordinate because it tells you how far and in which side, positive or negative, north or south of the reference point this any other point is. So in that sense, you can use this number line as a coordinate system for 1 dimensional space. Okay, keep this idea when we talk about the rectangular coordinate system. Now in a rectangular coordinate system, you are going to have 2 lines instead of 1. And generally, we use X for the horizontal, Y for the vertical line. We call them axes. Okay, so this is X-axis, the vertical is Y-axis. And there is a special point where they intersect, we call that origin, O. Okay. And so infinity on this side, negative infinity on the other side, infinity on the north side. Okay. In the normal compass mode, this will be east, west, north, south. Right. And south side is negative. Okay. We didn't write those infinities on the number lines, and those are extra things. Okay. We usually only write what I have done in red here, the X, Y, and oftentimes, the origin is denoted by O like that. And what else? Both of these are number lines, right? So that means there is a 0 somewhere on the number line. And in the standard position, we make those lines intersect at 0, both of them. Okay, hence that is called the origin. And now that 0, 0 represents 0 on X. The first 0 is on X, and the second 0 is on Y. Okay, 0 on X and 0 on Y. That will be called the point origin. Which means now, if I take any point, let's say here, I will be able to represent using 2 things. How much I traveled on X and how much I traveled on Y. In this example, let's say it could be 3, 2. 3 units, 2 units. Okay. And if you were to go to this side, you would be first moving left here on the horizontal, and then you would be moving upward in the vertical direction. So its coordinates would be negative 3, 2. Okay. So you can understand in a very similar way, if I am somewhere here, It could be something like -5, -1. Okay. I don't want that to look like I put it here. Or if we are somewhere here, let's say it could be 6, -1, right? Why? Because now you are going positive on the x and negative on the y, and you would represent these ordered pairs. What we call, we can use numbers like this to represent uh, point anywhere on that system, right? When you have developed these notations and these rules, how to represent every point using positive and negative numbers, horizontal, vertical, call it x-axis, y-axis. That whole thing is called the coordinate system. Okay. What is the advantage of coordinate system? It helps us talk about points on the plane. Okay. It helps us locate them, and I can, if I have to give directions to someone, I can tell, go to this point, and they will automatically understand whether it's north, south, east, west, because we have a convention, right? Okay. Two number lines at right angles. By the way, this is 90-degree here, creates this coordinate system, rectangular coordinate system. And I talked about the signs of those numbers in different parts, right? Those are called quadrants. And there is a convention again about that. When both are positive here, we call that first quadrant. Positive x, positive y. And then you go counterclockwise. Second quadrant is here. Third quadrant is here. Fourth quadrant is here. Okay. And every quadrant, the sign, of the coordinates is known, right? If it is positive and positive, that is your first quadrant. Look at the number here, okay? If it is positive and negative, yeah, this 6 minus 1, positive and negative, that is fourth quadrant. Negative and positive, like -3, 2 here, that is second quadrant. And if both are negative, as you can see here, -5, -1, that is third quadrant. Okay. All right. Here is a quick set of practice problems. Look at those points and identify in which quadrants they belong to. Pause the video, write your answers, and then check. 1, -3. This is fourth quadrant. Negative first and then positive. That is second quadrant. If you are going to go negative and again negative down, you will go to the third quadrant. And you might have wondered about this, right? 0, 2. Where is it? 0. So you are not moving on x-axis. 2. So you are only moving on y-axis. 0, 2 would be a point on the y-axis like that. So if the question is which quadrant it is it first quadrant or is it second quadrant? Normally we say no. Okay. Or you can say it is in between first and second quadrant. Or you can say simply it is on y-axis. The point is on the y-axis. When the x coordinate is 0, the point is on y-axis. Similarly, when the y coordinate is 0, you will get a point on the x-axis. Here, this point could be 6, 0. Okay. All right. So we talked about this coordinate system. In the coordinate system now, let's say, you draw graphs, and then we will be interested in things like if I'm at this point and if I have to go to that point, I want to go in the straight path and I want to take a break, when I have covered half the distance, right? How will I get that? At which point is the half the distance? The answer to that comes from the midpoint formula. As the name suggests, if you have a line segment, we call it, okay, from one point to another point, A to B, the coordinates of exactly in the middle is given by this midpoint formula. Okay, so here is a practice problem. You have these 3 points and find the coordinates of the midpoint. I will do the first one. Midpoint of AB. A is here, B is here, would be 4 plus, let me directly write, 4 minus 6 over 2 and minus 3 plus 6 over 2. Right? And you can simplify that. Minus 2 over 2, 3 over 2, or you would say negative 1, 3 over 2. Okay. That's the midpoint of the line segment AB. Go ahead and compute the next 2 midpoints and check your answers with me. I'm only going to write the answer. Do it and check it. Okay. BC, the coordinates of the midpoint would be 1, 3. And AC, the coordinates of the midpoint would be 6, negative 3 over 2. Okay. All right. Midpoint is one idea. Another idea is, what is the distance? If I travel from this point to that point on the coordinate system, how much length I am covering, right? And here's the formula for that. Again, we don't go into some of these details, but you can easily, intuitively understand. This is based on the Pythagoras theorem. Okay. I'll just leave it at that. If you have no idea about that, do the research. Okay. Distance formula and Pythagoras theorem. Search it. Okay. And what does it say? Subtract the x coordinates and square, subtract the y coordinates and square, add them and take the square root. We'll use that formula here now. Let's take the same triangle ABC. The length of AB will be under root. Now you can do this x1, x2 thing mentally. Okay. What is it? The first point, call it x1, y1. And the second point, you call it x2, y2. For your own reference. Okay. In your own mind, you do that. Or if you want, write it explicitly, whatever is comfortable for you. Then x1 minus x2 would be the x coordinate, 4 and negative 6. So 4 minus 6 whole squared plus y2. Okay. Okay. I have written x2 minus x1 in the formula and I did x1 minus x2, it looks like, but it doesn't matter. Okay. Because you are going to square it. And y2 minus y1 will be y2 is 6 minus y1 is negative 3. So minus and minus makes it plus. This time I skipped that parenthesis step. y2 minus y1, 6 minus minus 3. Okay, that becomes 6 plus 3. Make sure you follow that. Okay. So that will be under root 10 square plus 9 square And you can very easily see that is going to be 181. 100 plus 81, 181, which is irrational, right? That's the length of the side AB. Go ahead and compute the lengths of BC and AC. I will only write the answers here. Okay, and you check your work. Okay, BC is under root 232. If you computed it correctly. And about CA, you would have found that it is going to be equal to 5 at the end of it. Okay. How? Because initially when you use the formula, it would be AC, right? So 8 minus 4 squared, and 0 minus minus 3 becomes 0 plus 3 squared. And then it becomes under root 4 square plus 3 square, but that's 16 and 9, which is 25, and that is 5. Okay, so sometimes it gets simplified. Something like that was not possible for under root 232, although you can take something out of it. I'm not getting into that right now. Okay. Simplify when it is possible. Okay, that's all I would say. And related to this and on the same topic is this concept question. You computed the lengths of 3 sides of this triangle ABC. Now you answer the question, is that a right triangle? Okay. And hopefully this will also help you to remember or recall from your high school studies. Pythagoras theorem is when a square plus b square is equal to c square. That is how we usually remember it. Okay. So two sides, when you square them and add them, it should be equal to the square of the third side. Naturally, c is the longest here, right? The sum of the other things. Also what we call the hypotenuse. Okay. So we use that idea and try to figure this out. Here, this BC is like your C of that formula, okay? Because that's the largest, right? AB is under root 181, CA is under root 25. So if you compare them, under root 232 is BC. But what was BC squared? Is it equal to AB squared plus AC squared? No, you ask that question and you check. BC square will be 232. Basically, when you square, you get rid of the square root sign. AB square is 181. AC squared is 25. And you see that's not true. Okay. So the question is ABC a right triangle? Answer is no. Okay. All this to practice the distance formula really. Okay. Some more small topics on this line, until we get ready to start understanding what functions are. Many times you will have to do this rounding up while writing your answers. You might find these topics somehow disconnected. They're not, okay? I'm trying to connect them as much as possible. I hope you are seeing the flow of what I'm discussing here. But some of them are a little like individual topics, okay? Like that is this approximations. We are discussing that here because very soon you will be evaluating functions, you will be solving equations, and your answers will sometimes be in decimals, and sometimes there will be too many decimals, but we don't want to write all of them, right? So we need to approximate. So here we are going to talk about how to approximate what is called how to do rounding off. Okay. If you already know it, you can just write your answers there and move ahead. If not, follow me. Okay. Because this is something, sometimes emphasized a lot and taught in high school. So depending on, where you did your high school, you might already be comfortable. In that case, you can move on. Okay. I will demonstrate with this example. 6.75482. Right? Approximate it to 4 decimal places. 1, 2, 3, 4. 7, 5, 4, 8. But what is after 8? There is 2. So according to the rules of rounding, you just leave it, drop that 2. Why? Because 2 is less than 5. I'll talk about that. 3 decimal places, or sometimes we call near thousandth. That means we need to keep only the first 3. But what do I write? I write 6.75. Now I will write 5 instead of 4. And that is because what follows after 4 is 8, which is more than 5. Equal or more than 5. Okay. So 6.755. If you round up to only 2 decimal places, now you can go ahead and do it on your own first. These 2 decimal places. And you would say it is 6.75. Now be careful. Don't use this 5. Okay. You have to go back to your original value, which is 7542. 4 is less than 5. So we don't increase that. The last decimal, it will be 6.75. Also called 100th if you do 2 decimals. And if you do only 1 decimal approximation, that is 1/10th, nearest 10th. Okay. And in this case, the nearest 10th is going to be clearly 6.8. Because the digit after that is 5. Okay. 5 or more, then you increase the value of the previous digit. Okay. So here is a practice problem. Take this first few decimals of the pi, 3.14159, and do the approximations. Pause the video, do it, and check with me. 1000th should have been 3.142. 100th would be 3.14. 10th will be 3.1. And just the interior approximation will be 3. Okay. There are some more practice problems on this topic now. Is pi equals 3.14? If yes, explain. Is it rational? No. If no, explain. Okay. Answer is no. And the explanation is non-terminating. Decimals in pi. And 3.14 is only approximate value. That is the explanation. Okay. When I said no here, I mean answer is no. Okay. And then I was explaining. Next question. Name the possible quadrants in which the point xy can lie, in which the point can lie if the given condition is true. So what we are saying here is you take the coordinate system, let's say there is a point x comma y. Okay, will it satisfy these rules? Or what are the points, what are the quadrants that will satisfy that? Now the answer to this is the first quadrant, obviously, because if both are in the first quadrant, x and y, then x times y would be greater than 0, right? Positive. But remember, that's not the only time it happens. It could also happen if you are in the third quadrant, right? Both numbers are negative. So when you multiply them, you'll get positive value. So first quadrant and third quadrant, the product will be positive. Okay. Similarly, when you divide, multiplication and division, as far as signs are concerned, it's the same, right? So now you want the ratio to be negative. That means one number should be positive, the other should be negative. When does that happen? In second quadrant, you go negative and positive, or fourth quadrant, if you go positive and negative. So the answer here is second or fourth. Okay. And finally, in which quadrant is xy, the product equal to 0? And the answer is again very simple. Both xy, sorry, at least one of them, x or y, has to be 0 for the product to be 0. Think about that. You cannot take two non-zero numbers and multiply and get a 0, right? At least one of the original numbers has to be 0. But if one of the original numbers is 0, we are talking about being either on y-axis or on x-axis. Okay, so the question was name the possible quadrants. The answer is not on quadrants. Okay, those are on the axis, what you call coordinate axis, not in any quadrant. Let me put it that way. Okay. Here is another problem. You see the graph there, that is the graphical approach to this topic. From the graph, you can read the coordinates, and you're going to use that to do these two things. Find the distance and find the coordinates of the midpoint. Okay, if you are feeling comfortable, you can go ahead and do it on your own. Don't insist, but you can try it. The distance between P and Q would be, call it x2, y2, and this one x1, y1, mentally, okay, in your mind. Then x2 minus x1 will be 2 minus 3 whole squared, and y2 minus y1 would be -1, -4 whole squared, and a big under root for that. Okay, that is part A, finding the distance. You can simplify this, okay? This is going to be under root 25 plus 25, which is 50, which can be written as 5 root 2. Okay, that is the distance between P and Q. How does under root 50 become 5 root 2? Probably I will talk about that at a later point. Okay, it will be too many things in the same video. The coordinates of the midpoint. Coordinates of the midpoint of what? PQ. And the answer will be -3 plus 2 divided by 2 4 minus 1 divided by 2, which is negative 1 over 2. Okay. Here is an application problem. Distance between cars. Read it and try to draw your sketch. Check with me. Let's say, these are the cars. One is traveling north and the other one is traveling west. Okay, so I'm thinking maybe should move this line like that. I'm thinking about it strategically. Okay, this car A is traveling north in this direction. Okay, by the way, this will be north, south, east, and west here. And located 50 miles south of car B. Oh, it's 50 miles south of car B. So, okay, a little bit correction on the way I was representing. I'm going to move this up. Okay, and you'll ask me why, because it says the car A is traveling north, but it is located south of car B, right? So car A is here and is going towards north, and the distance from car B is here. Okay, and this is 50 miles. And car B is traveling west. This is the direction of car B, and the speed is 20 miles per hour. Okay. Let 0, 0 be the coordinates of car B. Oh, okay. So I did that already. And on the XY plane, where the units are in map. Plot the location of each car at 9 a.m. and 11 a.m. Okay. So at 9 a.m., what I have plotted in black color here is at 9 a.m. At 11 a.m., what happens? Okay, maybe I will draw a different diagram for that just for convenience. Okay, at 11 a.m., car A would have traveled, speed is 50 miles per hour. So from 9 a.m. to 10 a.m., it would have reached the origin, 50 miles. Then another 50 miles at 11 a.m. Okay, that is car A at 11 a.m. This is 9 a.m. Here we are at 11 a.m. And then what about car B? It is traveling at 20 miles per hour. So if A has reached there, it would have reached somewhere here, negative 40, 0. Right? Find the distance between the cars at 11 a.m. So the question is, what is the distance from A to B? Okay, plot the locations. We already did that activity here. For the second part, find the distance between cars at 11 a.m. Use the distance formula. Under root x2 minus x1. 0 minus minus 40. So anyway, minus 40 whole squared plus 50 minus 0 whole square. Okay, is x2 minus x1 whole squared plus y2 minus y1 whole squared. And that you can simplify, becomes 1600 plus 2500, that is 4100. So that is 10 root under 41. Okay, units. Now, unless the question asks, you leave it like that. If you have to do 2 decimal approximation, then you use a calculator, okay, and do the approximation. All right. That brings us to the end of the first section in module 1, in which we studied about the number systems and the coordinate system. Okay. In the next video, we will talk about linear functions. See you there.